All right, there you have it. There is our full design, our full answer to the system design interview question, how to design YouTube. All right, welcome back, everyone. We've been doing our best to post once a week on this channel, and the reception has been incredible. But I have seen several of the comments that are coming in asking for more of the long form problem breakdowns like we did in the beginning. So I decided this week I'd do exactly that. I'd hop on here and walk you guys through the really common system design interview question, how to design YouTube. And so this is not only super popular, but all the concepts that we're going to learn here apply to questions like design Netflix, design Hulu, even design Spotify to some large degree. So hopefully this is super informative. Quickly, I'm Evan, former Meta staff engineer, co-founder of Hello Interview. Hello Interview is a platform that helps people just like you prepare for upcoming software engineering interviews. And so if you haven't already, head over there and check it out. What are you waiting for? It's got everything you need. Now, if videos aren't your thing, we do have a detailed written write-up on this problem. Let me show you that one here, as well as 25 others. And the overwhelming majority of these are free. So as you can see, lots of content here on key technologies, question breakdowns. Come over and check it out. And you can actually practice the problem yourself. And so this will take you to what we call guided practice. You can answer questions by drawing directly on this whiteboard and getting instant feedback on how you did and how you can improve. So check that out if you haven't already. Lastly, as you can hear in my voice, I got a little bit of a cold, so apologies that my voice is a little funny throughout, but hopefully it's not too much of a deterrent. Let's get after it. All right, before we actually jump into designing the system, let's talk about the framework that we're going to follow both in this video, and this is the framework that we suggest that you follow for any of your system design interviews. And so if you've watched any of our videos in the past, this is probably redundant to you. You know this, you can fast forward. But for anyone who's new or anyone who wants a refresher, the first thing that you're going to do when you get a system design question is you're going to start with the requirements. And this includes two things. A, the functional requirements. These are the features of the systems, like users should be able to statements. Next is your non-functional requirements. These are the qualities of the system. So things like scalability, low latency, reliability, fault tolerance, etc. From there, you're going to move on to your core entities. Your core entities are the nouns of your system. Like if you have tables, these are the tables themselves. This is the data that is persisted and exchanged. And so, for example, on something like Twitter, this would be a post, a user, something like this. From there, we move on to the API. This is the contract with our users. So these are the external APIs that users are going to call in order to interface with our system. And this oftentimes exchanges the nouns of your system or those core entities. So data flow is more relevant for data processing question. We're going to skip that one because it won't apply here. So once we have the APIs in place, we move over to the high-level design. The goal of the high-level design is to satisfy those functional requirements. So this is a really simple design that is able to meet the user features. Not worried about scale, latency, or any of these things just yet. But once we have that simple high-level design down is when we get into the fun stuff. We go to the deep dives, and here we go one by one through our non-functional requirements in order to make sure that our system can scale, is low latency, fault tolerant, durable, whatever we put in our non-functional requirements. This is where we make sure that our system can handle those qualities effectively. All right, so let's get started. Maybe really quickly before I go over the functional requirements too, we should say, what is YouTube? The fact that all of you are watching this on YouTube means that I probably don't have to say anything here. But of course, YouTube's a video sharing platform. It allows users to upload, view, interact with video content. Fun fact, YouTube is, as of the creating of this YouTube video, the second most visited website in the world. So with that, let's get started on our functional requirements, that first step. So our functional requirements, let me make sure that this is in the font that you guys all prefer. Some of you have told me that this one is hard to read. So we'll go with that one. And so these are our users should be able to statements. These are the features of the system. And so in the case of YouTube, the first thing is that users should be able to upload videos. Of course, that's straightforward and necessary. The second is that users should be able to watch or download or stream videos. So users should be able to watch/stream videos. Those are our two main requirements from the user's perspective. That's what we're going to be doing today. Now, before we get right into the non-functional requirements, it's usually smart at this point to ask your interviewer about the scale of the system and make some potentially estimates around the scale, assuming they haven't already told you. And so if I'm the interviewer and somebody asks me as I'm designing YouTube, well, what is the scale? What are we working with here? I would tell them that we have about 1 million uploads every single day, that we have about 100 million daily active users, and that the max video size, and this will end up being important to our design, is 256 gigabytes. This is actually true of real YouTube. YouTube is a max video size of 256 gigabytes or 12 hours. And so with that, we can move on to our non-functional requirements. Again, these are the qualities of the system. And so if you struggle to come up with non-functional requirements on our website, if you go to the Learn tab, System Design, and then Framework, it's going to give you a list of all the things you should consider when you think about non-functional requirements, all those ILI statements that you should be thinking about here. But the first thing that we typically want to do is we want to consider cap theorem. And so is our system going to prioritize availability, or is our system going to prioritize consistency? Because partition tolerance in a distributed system is always a given, right? And so when we think about this, particularly as it pertains to uploading and viewing videos, when I upload a new video in, say, Germany, is the expectation that a user in the United States sees this instantly and immediately or gets an error? And the answer is, of course, no. It's fine for me to upload a video in Germany and it take a couple seconds to minutes to maybe even hours for a user in America to see it. And so as a result, we're going to prioritize availability over consistency. It's far more important that users are able to see the current content on our site, watch videos, etc., even if video uploads themselves are eventually consistent. It takes them a minute to propagate to everybody. So availability over consistency for video uploads. Now, the next thing that we want to consider is that we talked about 256 gigabytes. That's a ton. And so we should call out in our non-functional requirements that we need to support uploading and streaming for large videos. Specifically in our case, 256 gigabytes. That's going to be an interesting challenge for us to pay attention to. Remove that. And then we also want to make sure that streaming is low latency. So we typically think about latency in situations like this, and we want low latency streaming. So when I click watch a video, I should see pixels on my screen pretty quickly. We'll say maybe 500 milliseconds is what we're going to shoot for. And then this should also be true in low bandwidth as well. And so even if I'm on a bad connection, I still want to get pixels on my screen ASAP. And then the last one, which is almost always true, is that scalability. So we want scalability to scale to 1 million uploads per day and 100 million views, right? So at the end of our design here together, and at the end of your design in a real system design interview, you're going to want to look back at these things and say, did I meet all of these functional requirements? And does my system satisfy all of these non-functional requirements, all these qualities of the system? And if you can do that, then you're going to be feeling really good. So with our requirements in place, now it's time for us to move on to both the core entities and the API. And so as a reminder, those core entities, these are just like the tables. These are the entities. These are the nouns that are going to be persisted, saved in your database, and exchanged via your APIs. And so some guides will recommend that you outline the entire schema, the entire data schema, this early in the design. You can do that if you feel comfortable doing so, by all means. For me, I find that sometimes I struggle to know the full schema when I'm this early in the design because I just don't have the context yet. And so instead, I like to just orient myself around what are those core entities that we're going to need. And then I'm going to go into detail on the schemas later in the high-level design. And I'll usually proactively explain this to my interviewer as well. But in the case of YouTube, what are our core entities? Well, the main core entity is, of course, a video. This is the thing that is uploaded, downloaded, watched, streamed, etc. Of course, there's also a user. This is the person who's doing the uploading, streaming, or watching. So we would have a video table and a user table. Now, this might not have come immediately to you, and maybe this is a bit of mind reading because I know where this is going to go. But videos themselves are made up of like two parts. They have the bytes of the video, the actual thing that you watch. And then they have the video metadata. This is like the title of the video, the description of the video, the things that you input when you upload it, the privacy settings, what all of this is going to be out of scope for us. And these two things are stored and handled differently. And so I know this. I'm going to split them up in my core entities. I'm going to have video, which is the raw bytes, the actual video information, as well as the video metadata and the user. Those are my core entities. Now, going on to the API. When you get to the API, it's actually straightforward. You're going to want to just come to your functional requirements and go one by one through them. making sure that you have APIs to satisfy each of them respectively. And so our first functional requirement is users should be able to upload a video. Cool. So let's have an API endpoint for uploading a video. And so we can have some post endpoint that hits the videos resource. If you want to have versioning, any of that, feel free to add. It's not the most important thing to me. And then what we're going to pass in via the post body is the raw bytes of the video, our video's core entity, as well as the video metadata. Those two things are going to be passed in at the same time. And so a quick call out, if you have some experience uploading large files over post requests, you're actually going to know that this isn't going to work for our 256 gigabytes. This is only going to work for small videos. There's a limit by either API gateways, by servers, etc., whichever hardware you're using. There's going to be a limit on the size of your post body. And most likely we're going to be larger than that limit. But this is a reasonable place to start, and you'll see later in our design that we come back and we amend and we improve here. Now, the next one of those functional requirements was that users should be able to watch or stream a video. And so we'll add watch a video, and we need an endpoint for this. And this can start simply as just get videos. We'll get the video ID, and this is going to return to us the raw bytes of the video for us to watch, as well as the video metadata for us to know the title, description, and the creator. And so those are the very basic high-level APIs that, as I said, we're going to come back to and improve in a moment. But at this point, we've done the setup. We know our requirements, we know our core entities, we know our APIs, and we're ready to get into the fun stuff and start actually drawing our high-level design. So when it comes to our high-level design, again, our goal is just to satisfy those core functional requirements. And given that we derived our APIs from the core functional requirements, it's really just to make sure that we can document through components how each user API request is going to flow through our system. And so let's do exactly that. We're going to start with users being able to upload videos, since that was our first requirement. We're going to come over here and start drawing. So the first thing is I'm going to have the client. This is the user's machine or browser that's going to be uploading the video. And then they're going to be interfacing with, we'll put an API gateway here. You see this in most of our designs. An API gateway is really just responsible for routing to the appropriate microservice. That's the most important thing that it does. And then it also does some middleware like authentication, rate limiting, etc. And so the client is going to hit our API gateway. It's going to then route us to, at first, our single service, which is going to be our video service, we'll call it. Our video service. And this video service then is going to be responsible for taking that video and video metadata and storing them respectively. And so I'll zoom in a little bit here, but we'll have two places to store our data. The first is that we're going to have a video metadata DB, and this is going to be something like, it could be Dynamo, it could be Postgres, it doesn't matter a ton, to be honest. There's not a lot of requirements on that. We don't have a ton of uploads, 1 million per day. But the video itself is going to be stored in blob storage. And so we could use S3, we could use, what is Google's equivalent called again? GCS, right? And so we can upload the actual video here. Boop, upload video. So upload video, and then store the actual video metadata here. Video, so store metadata. Cool. So straightforward enough. User makes a post request with both the video and the metadata. We store the video itself in blob storage in S3 because this is going to be much cheaper. And then we store the metadata in the video metadata DB. Now, as I alluded to earlier, and we might as well just cut to the chase, there's an issue here. And that's that most components have some maximum on the total number of megabytes that can be in a post request. And so for like an AWS API gateway, just to use it as an example, that maximum is 10 megabytes. And so we can't have any video that is larger than 10 megabytes. And of course, that's not going to cut it. And so I'm slightly jumping the gun here. This is something you could discuss in your deep dives. But given that it's such a glaring issue with our high-level design, I'm just going to take it head on right away. Note that this would be an expectation, maybe of a senior and a staff engineer. If you're junior or mid-level, there would really be no expectation for you to know this. You should know that the video itself needs to be in blob storage, and then the video metadata can be in a separate either relational or NoSQL database. But everything I'm talking about here is maybe just a little bit more advanced. And so our API gateway in our case is an Amazon AWS API gateway, a limit of 10 megabytes. And so we cannot upload our whole video in one shot. And so if you've watched our video on Dropbox, you understand the general strategy here. And that's that we're going to have to upload in chunks instead. And so fortunately, as opposed to uploading in chunks ourselves, stitching them in the video service, and then uploading to S3, which we absolutely could do, the more common pattern is that we can upload directly to S3. And so by uploading directly to S3, so upload directly to S3. By uploading directly to S3, we're not having to pass these bytes, sometimes a significant amount of bytes, through each of these components, right? And this is going to lead to network costs. It's going to lead to computation. And so instead, let's go right to S3. And then fortunately, S3 supports an API. And that API is called multi-part upload. Multi-part upload. And similar, GCS supports resumable uploads. It's the same general idea. But what multi-part upload does is it allows you to upload a file in chunks, and then all those chunks get to S3, and then S3 stitches it back together and has that full-formed video. And so the way that this actually works now is that when we want to upload a video, we're going to come back here to our API and we're going to update it. When we actually want to update a video, we're just going to update our video metadata. Or we're going to post our video metadata. And importantly, that video metadata is going to have the size of the video. And so we're going to come in here, we're going to store that video metadata, and then instead of uploading to S3, we're going to get pre-signed URLs. And so what these are is this telling S3, hey, I'm ready to upload a 1 gigabyte video file to you via multi-part upload. And so then S3 will say, okay, here you go. Here are, some 1,000 pre-signed URLs for you to put, like post, but in this case, they're actually a put each of your video chunks to, right? So here are all the URLs that you can use in order to put them into S3. And so the client then is going to get back all of those pre-signed URLs. And then on the client, we're going to chunk. And like AWS has via the SDK, a multi-part upload API that will do all of this chunking for you. So chunk and then put to those pre-signed URLs respectively. And so this is just going to upload them directly to S3 in chunks, and we don't have to go through this limit of 10 megabytes through our API gateway. Cool. And so then we end up with a question. And that question is, if we were to document what our video metadata is, it's going to have some ID for the video. It's going to have some of this basic stuff like name and description. But then it's going to have some status, some upload status, and this is initially going to be pending. And then it's going to want to know the S3 URL, like where's this actual video in S3? And so because we're uploading this way from the client, the question becomes, how do we tell this video metadata that our video has been uploaded and that we now have an S3 URL? And so once you complete multi-part upload, S3 is going to respond to the client saying, hey, I'm done now, and here's your URL. And the client could post to the video service and then we update it that way. But we'd be trusting the client. And in general, we don't really want to do that. And the reason being that the client could just lie to us. The client could decide to not tell us that something has been uploaded. And in doing so, we would land with an inconsistent state. And so instead, the best practice here is that S3 actually supports something that's called S3 notifications. S3 notifications. And so what it does is it basically just triggers a notification that some Lambda function or worker or server of any kind, I'm abstracting that, can take that notification. That notification is completed upload for a given video. And then it's going to tell you what that S3 URL is. And so we can take that, our worker can take that and come into our video metadata and update the status to upload complete or uploaded, right? And then update the S3 URL so that we actually have it now. And so, in short, this is how we would handle the basic upload path. So we can now handle uploading videos to YouTube. Let's look at our next functional requirement. The user should be able to watch or stream a video. And so the first easiest thing that we could do is that the client calls that GET request with a video ID. We look up the video metadata. We return to them the name, description, as well as the S3 URL. And that I can make this a double-sided arrow. They're going to download directly from S3 as well. And so to download directly from S3. So client made their GET request, they got back the metadata as well as the S3 URL, and then they download the video directly from S3. Now, again, clearly for large videos, this isn't going to work well, but let's save that for our very first deep dive. So as we get into our deep dives, as a reminder, the goal of our deep dives is to satisfy these non-functional requirements. And so the task is relatively straightforward. We're going to go one by one through our list of non-functional requirements and update our design until each of them are met. And so we can start here. I'm going to start with the second one, support uploading and streaming for large videos. We talked about upload already. I jumped the gun there a little bit, but I didn't want you guys to be left hanging with something that was inaccurate for too long. So we're going to focus on how we can support streaming large videos. And so our current design has it that we download directly from S3. Now this has some key limitations. Even if the video was 10 gigabytes large, which is quite large, but significantly smaller than our 256 gigabyte maximum, then when we want to download the entire video from S3, it's going to A, take a while, because we have a lot of data that we need to send over. B, it requires the client has like 10 gigabytes of free memory just sitting there ready for us to be able to use. We need the connection to be stable during the entire length of the download. There's a ton of limitations. The biggest being that first one, that I'm gonna have to wait, in some cases, minutes or even hours until I see the first pixels of a video. And I don't want that. I wanna click on it and I wanna see the video, right? And so the intuition here is actually very similar to what we did for uploads. And that's that we need to serve the client chunks of the video as opposed to the entire full video. And so once we have the video here in S3, we're going to need to rechunk it, store those chunks, and then send those chunks over to the client. And so what I can do here is I can add an additional component. This is going to be some worker that we call our chunker. And then when S3 completes, similar to how it did for updating the metadata, it's going to send our chunker an S3 notification saying, hey, I have a new video, I'm ready. And then that chunker is going to chunk it into these small 2 to 10 second clips. The smaller the better usually, but depends on the streaming technology that we're using. But 2 to 10 second clips. And then I'm going to store each of those clips back into S3. So store the chunks back in S3. And then I'm also going to go update my metadata. And so I'm also going to come here and update my video metadata such that now we don't store only just the S3 URL. Maybe we'll call this the full S3 URL. But we also store all of the chunks. And this is going to be a list of S3 URLs, an ordered list of the S3 URLs. Right? And so now when the client wants to watch a video, what we're going to do is we're going to get that list of chunks in the video metadata, which is going to be the ordered list of S3 URLs. And then we're going to request from S3 each of those respective chunks in like 2-second increments. And so what this is going to do is that instead of having to wait for an entire 10 gigabyte file to download, we're going to download just that first chunk. We can get pixels on your screen ASAP, and then in the background, we can be downloading the rest of those chunks. Now the question you might be asking is like, wasn't this redundant? We chunked on the client side in order to upload in chunks, and then we stitched it back together into a full video in S3. S3 does that itself. And then we rechunked only to store chunks in S3. Like, what the heck is going on here? And the reality is that these two chunks are optimized for different things, the upload and the download. And so they're different size chunks. For upload, these are like really large chunks. They're 5 to 10 megabytes in our cases. And the goal is to minimize the amount of HTTP request overhead. They have some arbitrary byte offsets. There's no consideration of the content boundaries for playback or anything like that. Whereas our streaming chunks are optimized for the playback experience. And so there are these small segments, these 2 to 10 second segments, so that we can get that quick start and adaptability. And they tend to be cut precisely at video keyframes for this clean playback. So smaller chunks, larger chunks, optimized for different things. That's why we chunk 2 different times. All right, so coming back over to our non-functional requirements, we can see that the next thing we need to worry about is low latency streaming. So less than 500 milliseconds to get that first pixel on the screen. I click a YouTube video and I start seeing video. And importantly, this should also be true in low bandwidth environments. And so by doing our chunking, we've satisfied that quick first pixels on the screen. We're low latency now. But importantly, we're not necessarily low latency in different bandwidths. And so I want you to think about it this way. What if you wanted to watch this YouTube video from like a bad cafe Wi-Fi or maybe even on 3G? And so let's imagine that you had a 2 megabits per second connection, a pretty awful connection, probably much worse than what you're watching this on. Then even one 2-second chunk of a 4K video could take 20 seconds for us to download. And so we certainly have not met our half a second latency requirement in that case, right? And so this is where we need something called transcoding. We need to transcode the video into a bunch of different bit rates such that we can send the user the optimal transcoding, the optimal bit rates, the optimal resolution, right? So that they can play a lower resolution video if they are in a lower bandwidth environment. And so before I get into all of that, let me just really quickly go over like what the heck is in a video file? That thing that we're storing in S3, what is it in the first place? And so I'm going to come over here and I'm going to paste something in. So the video file that we are storing is made up of a couple components. The first is the video container itself. And so this is like an MP4 or an MOV. This is what we're storing in S3, and this is what you know and you click on your computer. But this video container stores a couple of things. And the first thing that it does is it stores the video codec. And the video codec is just a method for compressing raw video, which would otherwise be massive. And so it's really cool. It works by identifying patterns or redundancies in visual data. And then instead of storing every single pixel in every single frame, it just stores the complete keyframes, occasionally like full images, the changes between frames, this is like your motion data, and then some instructions for reconstructing the frames. So it takes otherwise huge video data and makes them smaller. Pretty cool, right? And then the audio codec data we won't focus on as much, but it's a similar process, just for audio. And then there's a handful of parameters that are necessary for playback: bitrate, resolution, frame rate, aspect ratio, duration, all of that's in a video container too. And so this is useful to know. You would not at all need to say this necessarily in a system design interview. I want to be clear there. This is me just kind of teaching the concept so that you have the foundation. Instead, when you come back here, the intuition is just that we're going to need to create different codecs and different bit rates and different resolutions so that we can store smaller videos that can be played on devices with lower bandwidth. And so let me show you what that might end up looking like. After we chunk, we could do the following. We could have a transcoder whose job is to take that chunk and turn it into 4K. Presumably, maybe our video already started at 4K. We can't really upsample too easily, but bear with me, you'll get the picture. We'll have another one that handles 1080p. We'll have another one that handles 720p. Right? And so on all the way up the stack until we have one that's handling our super low resolution, maybe like a 240p, and then, everything in between. And so after we're done with chunking, we're going to go to each of these respectively. And in parallel, each of the transcodings of the chunks are going to take place. And then afterwards, they're going to go and be stored back in to our video metadata again. I'm going to move that guy down there. And so now our chunks is actually chunks by resolution, right? So we have different chunks for each of these respective resolutions. We have a list of chunks per resolution. And so if we looked at that maybe in like a JSON format, you would have something like this: 240p, and then a list of the S3 URLs for those chunks in order. The 720p, same thing. You get the picture, right? That's what that might end up looking like. And so we can handle those transcodings, and then of course, once transcoded, we're going to store those back in S3 as well. So store back in S3. And so all of this is happening asynchronously on video upload. The user uploads the video via S3 multi-part upload. Once the video is completely uploaded, it triggers an S3 notification. It hits the chunker chunks it, and then sends each of those chunks to the transcoders to create these different resolutions to alter the codec, bitrate, resolution, frame rate, etc., respectively. Store those back in S3, and then update our metadata such that when a user goes to watch our video, we send them this metadata, and they can make a determination based on their network conditions which S3 URLs they should download in order to get the video chunks at the correct resolution. Awesome. But what about if a user started watching a video at home, and maybe it was 4K. I have a 500 megabits per second connection. I'm sure you all are on something similar. But then I leave and I want to continue watching the video from my phone, and I've been downgraded to 3G, for example. And so this is where adaptive bitrate comes in. And so what the client can actually be doing is that we have code on the client such that it checks your network conditions. It goes and it grabs that 4K video and starts playing the first 2 chunks of the 4K video. But then instead of going and fetching more chunks for the 4K video, it's periodically reassessing the current network conditions on the client and adaptively fetching the subsequent chunks based on those conditions. And so it would recognize, okay, Evan's halfway through his last chunk of the 4K video, but his network connection is just downgraded to 3G. Instead of us going and getting more 4K chunks, let's give him some maybe 720p chunks so that he can watch this on 3G. So as we continue to make improvements here, we start to see maybe new problems or issues arising. And so what you might notice is that now our latency bottleneck is that we keep having to go all the way to S3. And so maybe your user is in, I don't know, Germany, they're on the East Coast, and your S3 is located in US West, so it's somewhere on the West Coast. And so this is a pretty long way for bytes to have to travel over the network. And so what we can do instead then is we can introduce a CDN over here. And what the CDN is going to do is it's going to have popular video chunks. And so instead of having to go back and forth, I'm a little cramped for space, sorry guys. Instead of having to go back and forth to S3, we can just download these directly from the CDN. And the CDN, of course, a content delivery network, these are servers that are located close to the users. And so we have lots of these things. They operate as a cache. And so if you're in New York, you would just be hitting a CDN close to you, maybe in the New York region, in order to get these chunks. And we're going to store just the popular videos from those regions in the respective CDNs. And then another thing that you can do is that this thing that we created here, this mapping of each resolution to the URLs, this thing's actually referred to in video streaming as a manifest file. And so this manifest file itself, it's just a file. It's just a file in like JSON, YAML, XML, something else, right? And it can be stored directly in the CDN too. And so now look at how easy it is to start streaming. In parallel, we can go ask the video metadata for the name, description, and whatnot. But while we're doing that, we just reach out to the CDN. We first download our manifest file, and then using our manifest file, we ask the CDN, okay, I'm 720p, I want the 720p stuff. And it comes right down from the CDN. And so now we're wicked quick. Like maybe we can even start streaming and showing pixels before the name or the description has showed up on the video. Right? Pretty cool. And so importantly, or maybe I should be careful. Maybe not importantly to an actual system design interview, but important to your intuition, is that everything that we just talked about, everything from designing segmentation methods for breaking videos into chunks, specifying the manifest file's format and listing of the chunks, the supporting of the multiple qualities, the enabling of the adaptive streaming on the client, all of this has been done. It's all been done by common streaming protocols. And so streaming protocols do all of this chunking and adaptive bitrate stuff for you. And there's 2 really common ones. There's HLS, which stands for HTTP Live Streaming. It was created by Apple. And then there's Dash. This is the main open source one. I think it's Dynamic Adaptive Streaming over HTTP. Don't quote me on that. I think that's what it is. And these guys do all of those things that we talked about. And they're designed to work over standard HTTPS, to work with CDNs, to know when to chunk, to know how to do the adaptive streaming and all of this. And so in an interview, do you need to know HLS and Dash? Of course not. Even a staff candidate doesn't necessarily need to know it. If you bring it up, is it cool? Maybe, sure. But the more important thing is that you understand the fundamental components of a streaming protocol. The fundamental components being that you need to chunk asynchronously, you need to transcode, and then you need to adaptively, based on network conditions, fetch a manifest file, and then adaptively, based on network conditions, use that manifest file to fetch the chunks and the subsequent chunks. And all of that is wrapped up in HLS or Dash, respectively. Okay, so taking a step back again, just let's make sure that we understand fully what's happening here. I know a lot of information has been thrown at you. And so when a user goes to upload a video, They upload the video directly to S3 using multi-part upload. So they chunk the video on the client, they send that video to S3. Asynchronously, when that video has completed uploading, we chunk it into smaller chunks than we uploaded it, into about 2-second clips. We transcode each of them into different resolutions. We store those resolutions back in S3, and then we also store in S3 then a manifest file, that's this thing, right? Explaining how these chunks can be used in order to be reconfigured into the actual video. And then when a user wants to actually watch the video, they're going to fetch that manifest file either from S3 directly if it's not popular, or from the CDN if it's something that we have cached in the CDN. And then they're going to use that manifest file in order to fetch the subsequent chunks at the right resolution and play them on the client. If they were to leave and go into a different bandwidth environment, the client is always adaptively fetching the next chunks based on the existing network conditions. And all of this are streaming protocols, either HLS or Dash. Awesome. So as we move towards the conclusion here, we can come back to our non-functional requirements. The availability over consistency, we've done this inherently by the fact that we have this asynchronous processing of the video. And this means that users aren't going to be able to see new videos until that asynchronous processing has actually completed. And that's fine because we stated eventual consistency was fine. We'd prefer availability, so they can just be watching the other videos until that process completes. So check mark there. Scalability, we want to scale to 1 million uploads per day and 100 million views. And so we can look at our system and say, where are our bottlenecks? Where would things need to scale? And so our video service is stateless. This can just scale horizontally any n number of times as needed. Our API gateway is also going to be serving as a load balancer to balance appropriately here. Alternatively, if you're using an open source gateway that doesn't have load balancing, you can just have a load balancer in front. Classic horizontal scaling, true in most system design interviews. Not the most interesting thing. S3, this is, in quotes, infinitely scalable. And so you can have huge amounts of data here. We're never going to reach that limit. We don't have any problems with anything going on with S3. For our video metadata, we have 1 million uploads per day. And then this is only like 1 kilobyte of data because our chunks by resolution, which is the majority of the data, is our manifest file, which we actually stored in S3 in the CDNs, if you remember. So we ended up removing this, and maybe I should do that for clarity. And so it's maybe just a kilobyte of data here. It's not a lot. Maybe over a year, 365 days, this is like, right, 0.35 terabytes of data over a year. Not a lot. Right? Obviously, we'll have some user information. Real YouTube has comments, likes, all these things that would blow this up. For our cases, there's not much going on here. This could honestly easily fit on a Postgres instance for many, many years. We could use DynamoDB here, and it would also only require a single shard. If our interviewer asks us about sharding, if this was DynamoDB, really, I guess any database, the same principle applies. We would probably shard by video ID. And then in the case of DynamoDB, we would do sort key on time. The combination of those two would be unique, but it would allow us to fetch the video, sort by time. We'd probably want a global secondary index on the user ID so you can get all videos from a given user, but that was outside of the scope of our current requirements, so no concern. Same too with the chunker and transcoding. These are stateless, so these can just scale horizontally. You'll add more and more and more of these as you need, ideally dynamically. And so when you configure these things in cloud services, you usually configure these containers to scale based on some threshold of either memory or CPU consumption. And so if over 80% of memory is used or over 70% of CPU, two made up numbers, then we would add more horizontal services for us to be able to continue to scale to whatever our needs are. The CDN, this is going to be maybe our expensive bit. It just depends on what we can afford as a company. If we're YouTube, we'll have CDNs everywhere and they're huge and they're going to store a bunch of data and life is good for us. But that's how we would handle the general scaling of the system. And so at the end of all of this, you have this fun design and we can come back and look at our functional requirements and say, can users upload videos? Yes. Can users watch and stream videos? Yes. Did we prioritize availability over consistency? In other words, was video upload eventually consistent? Yes. Can we support 256 gigabytes? Yes, both on upload via chunking and download via chunking. Do we have low latency streaming even in low bandwidth environments? Yes. We have our transcoders and our adaptive bitrate downloading here. And then can we scale to 1 million uploads a day and 100 million views? Yes. And so consequentially, we have a design that would pass the interview and everybody should be happy. Let me talk a little bit about what would be expected at each level though, because if you're a junior engineer and a mid-level engineer, you might be looking at this with your head spinning a little bit. And I totally get that. And so for mid-level engineers, the chances are that you're not going to have the intuition to know that you need to chunk on either side of this immediately. And so your interviewer is probably going to ask you some questions in order to lead you there. They're going to point out some things like, well, if I were to download a 10 gigabyte video, it would take this much time. Is there anything that you can do to make that quicker? And then you should be able to problem solve to understand that chunking is necessary. And so you might get to chunking, you might understand some CDNs, you may never even get to transcoding, and that's okay. Maybe they give you some hints about different bandwidths, and you realize at a really high level, oh, like I know about 240p to 4K, maybe I can just put these into different bandwidths, or resolutions, even without knowing the word transcoder. That would be fantastic for a mid-level interview. For a senior level interview, I expect a bit more intuition about the need to chunk here. I shouldn't need to probe you. You should understand multi-part upload. This is a really common process for uploading any large media. You should also understand just intuitively, even if you've never heard of any of these streaming protocols, and there would be no expectation that you have, that I would need a chunk in order to have a lower latency streaming environment. And then whether you get transcoding proactively or not, or it's something I hint at, maybe no big deal, but you should understand that idea. And then you should think about some of these optimizations with CDNs, manifest files, even if you don't know the word manifest file, of course. You should be able to answer my questions competently as the interviewer. For staff level candidates, again, I don't necessarily expect that you know HLS or Dash. These are things that only somebody who's worked on streaming products in the past would know. But I do expect that largely proactively you can get here. You understand proactively the need for chunking and transcoding. You have the intuition, of course, that you need to split up your video metadata in S3. And maybe even along the way, you teach me something. You teach me something that I didn't know about any of these given processes, whether that's a technology that I wasn't aware of, some way to handle this DAG here and retries and failures. That's something we didn't touch on, but what happens if the chunker fails? Right? That's an interesting part of the design that if you have enough time, a staff candidate totally might go into. All right, there you have it. There is our full design, our full answer to the system design interview question, how to design YouTube. I hope you enjoyed this. Go ahead and leave any comments. I try to respond to as many of those as I possibly can. Of course, stop by hellointerview.com, check out our content, our guided practice, our mock interviews, mentorship, everything you need there to prepare for your upcoming interviews. And most importantly, best of luck. I know it's a grind. You're in it. You're doing great. And you're going to crush. All right. Talk to you soon.